Next, we will go forward with the distributed training. So, as I was mentioning, that it is very easy to distribute the training in TensorFlow, but why we are using that you need to know, because um, the environment you are working with, you need some enhanced performance in the end. But actually, you need to also know the environment that you are working with, right? So the ideal performance you want to get, let's say, very fine-tuningly managing the entire pipeline of your training, defining. So we were mentioning something about this line in the last class, that you can fine-tune or finely manage which step will go to which GPU that is available for your system. But distributed APIs, if you are using that, you will get out of the box performance, which is essentially kind of equivalent if you are doing that fine-tuning. What does that mean? That means that using this simple API, just one line of code, you can distribute the training, but you'll get the same performance as if you were fine-tuning the each step of your training pipeline. Now, how it is happening, we will not go into that details, because in the backend, as I was mentioning, it is called, the core is actually developed with C++, and it's very close to system that language is very close to your system. So the performance you will get with the C++ backend is much higher than Python, right? So that way, using these APIs, you will get the same performance as if you are fine-tuning. Now, using these APIs also is versatile in nature, because the same strategy you can follow for different architectures, different hardwares, different APIs, as well as combination of them. Okay, so we will see a few instances of that. Now, distributed strategy essentially is the main class for that distributed strategy, and this strategy is used to distribute any model using Keras API or Estimator API. Now, again, in the previous class, so you just follow the sequences. In the previous class, we have said that you can define your models using Keras API or Estimator API, but Estimator API is not being maintained nowadays, so you can use only Keras API for efficient distributed manner. Now, distributed my model is also possible using a custom training loop. This is very simple, and also to get much more flexibility. Okay? So you can make your layer, your library, your infrastructure distributed aware. What is distributed aware, we will see, but you can make your different stages of defining your model. You can define which will be the distributed aware module for your case. So this is much more control. So TensorFlow is all about abstracting everything to opening everything to you. So that means high flexibility and high controllability. Okay, so both you can get. Make a new strategy. If you want a new strategy to distribute your training process, that also you can make it. And that is also quite valuable if you are targeting, let's say, multi-accelerator things. But again, some APIs are already there, which will help you to take advantage of different accelerators that are available in your system. Yeah, different API surfaces for each of the module that you'll see now. Now, this strategy, that first strategy we will talk about is the mirrored strategy. So mirrored strategy is the multi-GPU all reduced sync training. So it is all about synchronized training. Synchronized training means each of the devices where you are distributing the processes will be locked and executed. So, and all the APIs are maintaining everything for you. You do not need to worry about the global interrupt lock. So, uh, it is very efficient. So replicas of the variables that you want to distribute, that will be actually made replicas, and it will synchronize again at the gradient stage. So when you are trying to compute the gradient, then it will meet again, and so this is all stage where you are actually uh, distributing your variables to or making replicas in each device. So basically, let's say you have one system where you have one CPU and multiple GPUs. You want your replicas, that means replica of the variables that you want to distribute, will be available to all GPUs. That is all. And in the reduced stage, you're actually synchronized, right? So this is all reduced, and sync is essentially doing in lock state processes. Variables are mirrored in each GPU, as we were discussing here, and all reduced, this algorithm will actually do the aggregation of the gradients. So how it is doing it? So let's say we have this one device and second device here. And first device, we are giving the input. Here's the input 0 and another input 0, input 1. Now here we have the same layers A, B, A, and B, A. That is the backward bus, and this is the forward bus. Now I want to replicate the VA. So VA0 and VA1 has been, two instances have been created, which is replicated actually in the two devices here. Then the output for the second layer is VB0, VB1. Then we are doing the backward propagation. So now we want to have this VB0 and VB1 to be made in the middle somewhere where it will be aggregated. And again, so basically this is the reduced stage where it is reduced. The variables is, all variables will be reduced and then it will be distributed again. And then again, the gradient combination will happen, and again it will need to get the average of the delta, which will help you to improve the to update the weights for particular devices. So VA, del VA, which is computed here, will be broadcasted to all these GPUs. So this is the synchronous training. So you see here each. So this is locked also. This process is also locked, and you, until or unless you get this here, you do not know. You cannot do the reduced. So this is the synchronous training. Now all reduced synchronous training, how you can define it, the strategy. So mirrored strategy, that means making replicas, replica of variables. How you can define? This is one way of defining. Strategy is equal to tf.distribute dot mirrored strategy. Mirrored strategy is very simple function which will distribute your or mirror your variables to all the devices that is in. If you want to particularly define which are the devices that you want to work with, you can also give the arguments, which are the particular devices, GPU 0, GPU 1 in this case. And also you can define which reduce algorithm will be used. You can define that in the argument also. These are the three ways to define the strategy. Once you have defined the strategy, you can go to your model definition and completion. This is the sequential way of defining the model that you have seen so far. And to add like these variables which are used in these layers will be distributed to your machines. If I want to specify that, we'll just wrap this with this strategy.scope. That's it. So you define the strategy, you wrap your entire training module inside the strategy.scope. So this particular block is under this strategy's scope. That's it, simple. And you will have the mirror strategy with all reduce. That's simple. And this particular block, which you will see in this red box, is essentially the distributed error blocks or distributed error block. So distributed error block, you can also define that you have seen so far. So this is the distributed error block, because now now the backend knows that this is the block where I will mirror the variables. You can have multiple worker, so that was for single worker and multiple devices. You will have multiple worker, multiple devices, and in this case, TensorFlow corrective ops will be uploaded. Again, the thing will be synchronized in nature, and so workers will run in lockstep, and you will synchronize the gradients in each step. Okay, so each step will be distributed to multiple worker, multiple devices, whatever you define. So worker, which will do the things, okay. And this is again synchronous in nature. So how to define that? You want to distribute, use the multiple worker mirrored strategy. So this is coming under the experimental module. So this is just the experimental module, but it will be transferred to your mainstream module in any time. Okay, but you can use this tf.distribute.experimental.multi-worker mirror strategy to define one mirror strategy, which is will be creating one scope for your distributed module, which will be distributed to multiple worker and multiple devices. You can also define which backend communication will be happening. HCL you can define. Okay, RICE. Then you also need to define the workers, basically which will be the task type and the workers, and that will be given as JSON string form. Okay, so cluster, the specification for your nodes here. This will be the worker, and this will be. So this is the simple usage of a multi-worker mirrored strategy, where you can have multiple worker working tandem in a synchronous manner. In all the steps will be locked and executed. You can have all reduce synchronized training for TPUs as well. So it's a bit tricky, but since through the Colab also you have seen that you have the flexibility to access TPUs. It is similar to your mirror strategy, but unlike mirror strategy, it will use cross replica sum to synchronize the aggregations onto from different nodes. One TPU is TPU, and many TPUs is called TPU pods. Okay? So you can have both. So how to define this strategy? So again, as I was mentioning, that once you have defined this strategy, you can use strategy.scope and define your scope. Again, here we will define the strategy, and strategy.scope you will define your distribute error block. That's it. How you can define it? You can define your resolver, which is essentially cluster resolver class, and this will actually be using this TPU cluster resolver for the TPUs. Okay, so it's a bit tricky, but you can use these steps to use this strategy. Now, how you will get the strategy? You will just define to connect to the clusters, initialize the TPU system, and then use this resolver to create the strategies, right? So this is again coming under distribute.experimental module, where you will have this TPU strategy to be defined for your TPUs, and you can use this strategy using strategy.scope. So we have talked about synchronous execution, where your workers are working in a locked state, right? What happens if your workers, let's say multiple devices you have in one system, they are not similar in runtime performance. Let's say some worker will do faster, some worker will slower, and so on and so forth. So you will have different performance workers in your device or in your machine, and you can use parameter servers and workers in this case. Parameter servers maintains the global variables which will be actually synchronized and doing the aggregation. And worker nodes will again do the replication of the variables computing, and then it will send to the server parameter servers to get aggregated and get back. So parameter servers will take care of this synchronization. So these workers will be working in their own way. Okay, so this is a bit different from your synchronous way of working things. But once you have the APIs, you do not need to worry about anything. So the parameter server strategy, we are defining it with, again, it is coming under distribute.experimental and parameter server strategy. So you can define it, and you can uh, also define with parameter server strategy with these two ways. Okay, so this is just the name that we are doing. Now, once you have defined it, actually you can use the strategy as a scope, and also you need to define in the JSON string format the workers, which will be the PS, the parameter servers, and which will be the worker. So these two definitions, if you just give in the configuration string, that's it. So once you have this definition for the tasks and the cluster, so basically what nodes will be the worker and what are the nodes will be your parameter server. So that's it. One more way of approaching is central storage. So central storage is basically the one node approach of parameter server one, the PS worker strategy that you have seen. So this is asynchronous also, but we think that, so here we had multiple devices where we have defined which will be the parameter servers and which will be the workers. But here we are thinking from a single node point of view. In a single node, you will have multiple devices which are not exactly same in performance. So you can use central storage approach, where one machine, multiple GPU will have one copy of each variable will be in CPU. So maybe CPU will be working as a parameter server, right? And one replica of the model will be in each GPU here. And because it might so happen that parameters, the number of parameters, this is another case where the number of parameters is getting exceeded more than the memory that is available for your GPU. So what you will do, because you are doing the replica, you are maintaining the gradients, and then again you are sending back those. You are getting all the updated values, aggregated values again. So it might so happen all the embeddings may not fit your GPU memory. In that case, you can use your CPU to be working as that central storage, okay, and offload everything to your CPU and do release some of the memory pressure from the GPUs. So how you can define it? Again, it is very simple strategy equal to pf.distribute.experimental.central storage strategy, and that's it. So your one PC system will be working as your parameter server strategy, and you can use this strategy scope to define it. So these are the reference codes that is already implemented with the engineers from TensorFlow for getting to know more about this distribution strategy that is already implemented for several things that you can look for. We will go into now one demo for functional API to understand better some problem approach we will see. So what is the problem that we are referring to solve it with functional API? Mentioning I may have single input and multiple outputs, right? So one problem I am defining here. So you have seen the MNIST dataset so many times for now, which is essentially the dataset for your handwritten digits, right? So from 0 to 9, we have digits, and all the images from different way of writing it is there. Now I want to I want to create one model which will classify first, of course, the digit, whether the digit is 5 or 6 or 9 or 10 or 0 rather, and another head will predict whether this is being written in left hand or right hand. Okay? So this is the problem statement that we are targeting here. So again, one single input, one image you will give as input, and it will give two outputs. What is the number? Essentially 0 to 9, and whether the number is written with using right hand or left hand. Right? So keep the problem definition in mind, and we'll go forward with that model definition, how we will define such model, which will have two outputs, and then you will use the functional API. So simple inputs will define with Keras, let's say 28 by 28 image that is standard for your MNIST dataset. We are flattening this using this flatten keras.layers.flatten Keras API. Again, we are using all the imports up there. You can see first dense layer we are defining, which is dense layer, which is 120 output using activation ReLU function. Second dense layer, it is using 10 outputs and activation. So 10 outputs you can see here. This dense layer output is essentially will classify which digit is it. So we need 10 classes to classify. So 10 class and activation softmax function we are using because we need to classify in the end, because this will convert the logits into your predictions, and name is category output. So category of the digit that we have defined now this layer. You can name one layer. So this is just such use case where you can name the layer and you can see the layer definition of this layer. Now here we are creating two output layers, one output layer for the category output and another layer for left right output. So there is just one prediction output will be there because that will give you the sigmoid activation, and with this sigmoid activation we can get whether this is just binary classification we are doing here, right? Whether it is being written on left hand or right hand. So two heads we have defined. Now here we have defined the layers as functions. Now we will use these to call on the inputs. So now we are calling them, right? So X is flattening the inputs. So the input is flattened here because this is the fully connected layer we are using, dense layers. X equal to dense 1. So first dense layer. Then output 1 is taking this X as input and doing the 10 outputs. And this output 2 is taking this layer, basically this output of this layer. So same output is going to two heads and giving two outputs, right? So this is the important thing that in the function call functional API we can do it. This is the thing that I wanted to show you. Then you can define the module, keras.module inputs. One input we have, input equal to inputs, output equal to. Now you can see we are giving the output list here. So one model we have created now which has multiple outputs. So we are giving one list of outputs here, outputs 1, outputs 2, name equal to MNIST model. So you can define one model. So this is the name of the model. if I see the model summary, what I will see there is that input layer, this size, flattened layer, this size, dense one layer with this number of parameters, flattened one, which is the name, but category output one. So you see this name here, category output dense layer and category left right output dense layer. So these are the two output layers we have created, and so total. So this is the model definition, model summary, whatever you call it. Then we are defining two losses because two heads we have. So for the softmax, for this category loss, category output, we have this cross entropy loss, sparse categorical cross entropy loss from logits equal to false because we have defined the softmax activation. If you did not define the activation here, then you need the logits. So logits are the outputs directly coming from the neurons. Now, loss 2 is essentially again binary cross entropy loss because we are doing the binary classification. Optimizer we are defining, metrics we are defining, what metrics we want to see, accuracy we want to see. Two losses, one loss is for category output and second loss is for your left right output. So for two output layers, we have these two losses. We are comparing the model with this loss, whichever we have defined here with this optimizer and with this metrics. As simple as that. And we are training the module here. So basically, we are creating the data set here. So keeping the data sets as a source, we are taking the MNIST data set, creating train test modules, and then we are unpacking and normalizing the images here. Then we are creating the two classes. Let's say we are creating the two classes. Let's say greater than 5 will have written as, let's say, 1. Okay, so that is right-handed, and less than 5 is left-handed, let's say. Okay, so you can see here, so all these digits 500040, but 91 61. So all these are written in right hand and these are written in left. So now our class labels are being created. Then we are going into training to just call fit with this train function, train data set. This number of the epochs, batch size, levels 2. So now we are getting the outputs here for the accuracy loss and for different epochs. And we are doing the predictions in the end. And this prediction is essentially calling on the test. And how many predictions we are doing? 2 predictions. First prediction is for your left hand right category and then left hand right hand. And let's say we are taking the first 20 data and checking what is the maximum prediction for that and what is the left hand and right hand prediction for that. Printing the data, the labels with let's say category and the labels for your left hand right. So all the digits have been successfully categorized. So these are the predicted labels and predicted labels for the left hand right hand. You can see 1 is for your 7, 0 is for 2, 9, 5, 1. This is wrong prediction. But again, anyway, so you have seen how you can use functional API to simply define your module with different number of outputs, and you can train the module and extract the predictions and do so. As simple as that. So if you're doing transfer learning or maybe multi-head or multi-stage training, you are creating the pipeline, this is the best way to go using functional API. So with this functional API, we'll close this session.